Okay, so the big things to remember, guys, about centripetal force, okay, is that centripetal force is affected by mass. It is affected by mass linearly. Right? The more mass I have moving in the circle, the more centripetal force will be required to keep it in. It is affected by the speed at which the object is moving around in the vertical circle, and that affects it exponentially. So if I double my speed, I'll need 4 times as much centripetal force. And it is affected inversely by radius. Okay, that is, the larger the circle, the less centripetal force is required to keep the object moving in the circle. Okay, so those are things to remember. For the most part, our problem solving is going to involve the fact that FC is really the net force. Okay, the net force to keep something moving in a circle has to be directed towards the center, which means it's kind of the sum of all forces. Most of the time, it's just one force. So our challenge is to figure out what is FC equal to. Okay, what force is providing the centripetal force? Thus far, we've really only gone over unbanked curves as an example of that. And what holds you in an unbanked curve? Friction. Okay, so in this case, in the case of a banked curve, okay, we would say, or an unbanked curve, sorry, we would say that FC equals the force of friction, and then we would set their formulas equal to each other. mv squared over r equals mu times the normal force, which on an unbanked corner is the force of gravity. Okay, if I was looking at something that was being held in place by the force of gravity, okay, then I would have mv squared over r equals m times g. Right? I just set centripetal force equal to whatever force is providing it. Okay? Everybody follow me on that. No different than what we would have done in Unit 2 when we would have said m times a equals the sum of all forces. Right? And we would add all the forces together over there. Okay? Ringing a bell. All right. So I want you to work on a few more questions from the worksheet. I'll put it back up on the board here, okay? But I am going to stop you here and there and go over just some other examples just so we see a few other things and get a little break from you just sitting there doing that, okay? But we do need to practice it, so that's what we're going to work on for at least the start of today. Okay? Okay, so for number 6, we have an unbanked curve. And as soon as we see unbanked curve, we need to write down what's providing the centripetal force, force of friction. Okay, our other givens are the mass of the car, although that's not going to be important. Okay, the speed and the radius of the curve. All right, so we're looking for the coefficient of friction. We're looking for mu. All right, since this is our setup, okay, we can say then that mv squared over r, so centripetal force, equals the force of friction, mu times the normal force, which on a level surface is equal to gravity. Okay, so if I'm looking for mu, then I'm going to divide mg over to the other side. And when I do that, the m's cancel, and I'm left with v squared over rg, right? Which we noticed yesterday is the same as the bank curve formula, right? In this case, we're solving for the thing that keeps mu in an unbanked corner, and when in a bank curve, we solve for theta with exactly the same formula. All right, so we're going to solve for mu here by going 25 squared divided by, and then the bottom needs to be in brackets, so 72 times 9.81. If you don't bracket the bottom, it doesn't come out right. Okay, so we got 25 squared divided by 72 times 9.81. Okay, so we get a coefficient of friction of 0.88. Okay. Any other ones giving us trouble? Okay, so this is a bank curve question. Okay. So we have an airplane traveling at a speed of 115 meters per second, so we know v, okay, and it makes a complete horizontal turn, so one circle, in 2 minutes, 1.20, so 120 seconds. Sorry, that's big T. Okay, so what's the banking angle? So we're looking for theta, okay, so that's our question mark. So our bank curve formula is that the tan of theta equals v squared over r times g. Okay, but what I don't have is r. But because I have V and T, I could find it, right? And that's what I'm going to have to do here, okay, is plug into this formula here, V equals 2 pi r over T, in order to get R, right? So I'm going to multiply both sides by T and then divide both sides by 2 pi, and that'll give me R, okay? So then I can have that to use in my formula. So we'll have 120 times 115, okay, divided by 2 pi. All right, so now we have our radius just under 2,200 meters. Okay, so now we can use that in the tan of theta formula. Okay, so to manipulate this for theta, I'm just going to go theta equals tan to the minus 1 of v squared over rg. Okay, plug in my numbers, so tan to the minus 1 of 115 squared divided by 2196. I'll put all the decimals in when I actually calculate it. Okay, times 9.81. Okay, so we got second 10, right? And we're going to have 115 squared divided by, and the bottom has to be bracketed. So I'll take my answer times 9.81. Okay, so we're looking at a banking angle of 31.5 degrees or 32 degrees, 31.5. Yep. Any other ones giving us trouble there, guys? Okay, so how did we do with number 8? Because number 8 often gives people trouble, the one with the phonograph. Yeah? Okay, because like, do you guys even know what a phonograph is? Okay. It's not unusual for you guys to, this is like a generation gap question. It's a record player. Right? You know those big black vinyl things that they used to put music on? Yeah, so they put those, it spins them around. And there's two different kinds. There's the kind that go around at 33 1/3 revolutions per minute. They're the big ones. And then there's little ones called 45s. They're about half the size and they spin faster. Yeah, I don't know why they had to have two different kinds. It's not like the 45s were any more portable than the big ones were. It's not like you could, put them in your car stereo or anything. That's what 8-tracks were for. And you guys are probably going, what's an 8-track? It's a big giant tape. It was like this big. That's right. They had more space on them. You're right. That's what they were for. 45s were for singles. Okay. It was like ancient iTunes. You could buy one song if you bought just a 45 instead of the whole record. Anyway, okay. So for number 8 here, let's just have a look at that one as well. So what number 8 gives us is the frequency. It gives us F, 33 1/3. Okay, so it's 33 1/3 RPMs, rotations per minute. Okay, and the diameter of the record is 30 centimeters. But what do I want? I want it in meters, and I also want it to be radius and not diameter. Remember, that's that one trick that they can always try to play on you. Okay, so the radius is going to be 0.15 meters. I probably also want this, not in revolutions per minute, but in revolutions per second. So I'm going to divide that by 60 just so that I have that as well. So 33 point, and then we'll just put lots of threes, divided by 60. All right, so it's just under or just over a half of a revolution every second. So we have that number as well. So 0.55. Okay, that'll be hertz. Okay, now that I have that, okay, I'm looking for both the speed and the acceleration, okay, of a point on the circumference of an old style phonograph. So I'm looking for speed. Well, I can calculate that right now because I can just go 2 times pi times r times f. Remember, that's a manipulation of this formula here, okay, because f is 1 over t. So I can just multiply. So 2 times pi times 0.15 times 0.5 repeating, okay, will give me my speed of the record. So 2 times pi times 0.15 times our answer times 0.5. Sorry, I already got that. Times our answer. Okay, so we're moving at 0.524 meters per second. at that point on the record. And now that I have that, I can calculate the centripetal acceleration, AC. Okay? AC is v squared over r. So all I have to do is solve for AC by plugging in the numbers. Okay, the answer I just got, 0.524, divided by the radius, which was 0.15. Oh, sorry, I got to square it. My answer squared, not to the minus 1, squared. Okay, divided by 0.15. All right, we get 1.83 meters per second squared for the acceleration on that one. Okay, so that one's just mostly a context problem. When people read it, they don't know what a phonograph is, so they have no context in which to solve that problem. Okay, what was the other one I wanted to look at? Okay, I think we've done ones like the ones I wanted to do, but I want to actually look over number 12 as well. Okay, so we'll look at that one. Because bank curves, they just seem to come up a lot. Okay. So we got a 745 meter curve. So we know what R is, 745 meters. Okay, and we're looking for how much it needs to be banked. So again, we're looking for the angle here. It's traveling at cars are traveling at 90 meters per second, which is ridiculous. It must be a racetrack. Oh, it is a racetrack. Okay. What angle should it be banked if it's going to be used under very icy conditions? So this is like crazy racing on an icy track. Okay. Well, it sounds like fun. Yeah. You know, if you don't, mind possibly being in a mangling accident of some kind. All right. So we got tan of theta equals v squared over r times g. And again, the thing that throws people here is having to move the tan over. Okay. Looking for theta here. So theta will be tan to the minus 1 of v squared over rg. So this one's actually a little easier than the one that gave us the period, and we had to get r from that. Okay, so we'll have tan to the minus 1 of 90 squared divided by 745 times 9.81. The other thing that throws people on this question is that it mentions friction when friction's not a factor for bank curves. Okay, and that often throws people as well. When they read the question, they start thinking unbanked corner and they solve it wrong. Okay, so we're looking for theta there. We have our formula all figured out. So we're going to have second tan of 90 squared. And again, the bottom has to be in brackets or this doesn't come out right. 745 times 9.81. Okay, so we get 47.9 degrees above the horizontal. Okay, for our angle of bank. That is a wickedly banked corner. It is closer to vertical than horizontal. So really, really steep. You would have to go really fast, 90 meters per second, to stay in that corner and not slide into the middle. All right, questions on any of that stuff there? All right, reminder that your dynamics projects are due next week. Okay, they are due on Wednesday of next week, so make sure you are getting those done or at least having a look at them over the weekends, okay, so that you're not slammed next week.